So it's on now.
How close are you talking? Yeah. Standard.
Hey, Liam.
Oh, good to see you. I won't be saying anything today, Shanta. Yeah.
All right, let's get started with the next session. So we're happy to welcome our final new lecturer of the week. Welcome our final new lecturer of the week, Liam McAllister, who's going to tell us about de Sitter Vacua. So take it away, Liam.
Thank you, Oliver, and thanks to all the organizers for inviting me to speak here. It's a great privilege to address all of you. I'm going to talk about candidate de Sitter Vacua. And the goal for today's lecture is to arrive at this summary and understand its meaning, and also to spend some time figuring out what we want to do and why we're going to go about it the way that I'll go about it. So the plan of the 4 lectures is as follows. The first lecture today is about vacuum solutions, that is to say Calabi-Yau compactifications of superstring theory. And that's material roughly from the 80s and 90s. The second lecture will be about classical flux compactifications. That's early 2000s. Third lecture, quantum flux compactification, so early 2000s onward. And in the final lecture, I'll finally put the pieces together and describe a candidate de Sitter vacuum of string theory. So I've posted notes co-written with Andreas Schachner, and the notes that have been posted so far cover up through the end of pretty much the second lecture. The notes have a lot more detail than I have any intention of putting on the board, so if you want to check how various things arise, you can look there. Okay, so the goal of the lectures overall is to present and explain a class of compactifications of string theory that give rise to 4-dimensional cosmologies. As far as background, I expect that you have, of course, knowledge of quantum field theory and GR. As far as string theory, it would be great if you know some. If you have some cultural familiarity with the genus expansion and the alpha prime expansion, that's probably most of what you need. And then also the bosonic content, the massless bosonic content of the superstring. If you need a reminder on that, there's details in the notes. And there's also a crash course on complex geometry in the notes. Okay, so our goal in the line of work is to understand quantum gravity in the observed universe. And in particular, to try to relate quantum gravity to experiments in some way. So in particular, we'd like to know, what do terrestrial, astrophysical, cosmological experiments tell us about how quantum gravity works? And is there anything that we can learn by thinking about theories of quantum gravity that can make forecasts or influence design of future experiments? So we'd like to somehow link quantum gravity to experiment, all kinds of experiments. And so let's just begin with the most basic facts about the observed universe. These are facts that are well known to you, but we need to repeat them to stress what we're going to try to achieve. So the observed universe is 3+1 dimensional. It's large, it's flat, and it's old, and it's dominated by dark energy, which may be a cosmological constant or may not be. The universe emerged from a period of inflation or something very much like inflation at very early times. And finally, the universe is non-supersymmetric. Actually, that wasn't the final one. One more thing we need. It includes a sector. Maybe this is not the with the standard model, gauge group, and chiral fermions. And the point of telling you all these known facts here is just to say that any more detail than this, and we're going to exceed what we can really manage with string theory. So we're just going to try to get this very broad picture. So the goal for the near future, not just in these lectures, but generally in string phenomenology, is to try to relate quantum gravity to experiment very roughly, starting at this level, and not trying to make any finer predictions till we get a little bit more advanced. Now, in the work that I'll be describing, we're going to find solutions that are 3+1 dimensional, in principle are large and flat and could be old and have dark energy. We're not going to build inflationary models. They will be non-supersymmetric, and I'm not going to build the standard model in these lectures. Okay, so we're just talking about the dark sector. We're talking about the cosmological sector. We're just trying to build a model of de Sitter space, period. If you could build that, you could do a lot of interesting things. For example, understand the dynamics of inflation. Because inflation, after all, is a sort of a deformation of de Sitter space. So we first better build the foundations. Now, we're not going to get to de Sitter until the very end. And I'm not going to be able to tell you a lot of new things about the physics of de Sitter space in string theory. The goal of the line of work and the lectures is to build examples from which future workers can learn things about the physics of de Sitter space in string theory. Okay, so what I mostly have to tell you in these lectures is what are the basic objects that we put together and how do we find vacua. I should have said, normally when I begin these lectures, I ask people to feel free to interrupt. Of course, since I saw yesterday, that probably is not necessary. You'll probably jump in. But anyway, any questions at this point about the plan before we start doing actual things? Yes? Yankee.
Large and old relative to what?
Compared to a string.
Could you repeat the question?
Yeah, sorry. The question is, what do I mean by large and old? And what I mean is large and old compared to a string. In other words, that we're talking about a theory which we understand very well has a fixed fundamental scale in it, string scale, or let's say the Planck scale. And the basic feature about the universe that we should try hardest to explain, besides the fact that it's 3+1 dimensional, is that it's much bigger than the fundamental scale, fundamental length scale. Okay, that's the cosmological constant problem, and I'm just saying that that's like a key feature that we need to deal with. Thank you. Other questions? Okay. So we want to go somehow into quantum gravity, and how are we going to do that? We need a theory of quantum gravity, and of course the one we're going to use, the only practical one in hand now, which is string theory. And string theory can furnish, in some cases, weakly coupled UV completions of gravity.
Question, sir.
Of course.
So you said dark energy could be a cosmological constant or not.
Yeah.
But focusing on de Sitter, are we assuming that it is a cosmological constant?
Yeah. Good, thanks. Okay, question is, are we, by focusing on de Sitter, discounting the possibility temporarily that the dark energy is dynamical? Yes, but for the same reason that we're not talking about inflation, even though I love inflation. The reason is build a static configuration first to understand it, then mess it up. So that's why we won't get to quintessence in these lectures. Yeah, thanks. Okay, so string theory, the most important thing about string theory from my point of view is that it can yield weakly coupled UV completions of four-dimensional GR coupled to matter fields. That's what we mean when we say it's a theory of quantum gravity. Weakly coupled, It's going to be important because we don't just want to be able to point to it and say, well, this is quantized. We want to be. And as we will see, it requires building up a certain amount of technology to really do the computations, but it's the weak coupling that's going to be critical to make that possible. Not everything I say in these lectures will be perturbative or weakly coupled, but a lot will be. Okay, so much of what we know about string theory is, well, perturbative. Not all, but a lot. An awful lot of it is on shell. And a lot of it is in flat space-time or in ADS, rather than in more complicated spacetimes. A lot of what we know involves extended, let's say, 4-dimensional n greater than or equal to 2 supersymmetry. So a lot of supersymmetry. When I count supersymmetries, we're almost always going to be in 4 dimensions, so my curly ends mean 4D counting of supercharges. And frankly, a lot of what we know about string theory occurs in space-time dimension not equal to 4. But we want d equals 4, and we want n equals 0 supersymmetry. And so we got to find a way to get there. Okay, and so the idea, this is not an idea that's new to us, a very old idea, is that you can productively study n equals 0 theory by building on theories with more supersymmetry. And so what we're going to do in the course of these lectures is gradually go from 4D n equals 2 today, to 4D n equals 1 tomorrow, and then to 4D n equals 0 by Friday. And at each step, we're going to need to use, not just as a warm-up, but actually use content from the previous step to build the calculations for the subsequent step. Okay, so most of the work in this field then, of string compactifications, occurs in the following main setting based on this. We're going to be studying solutions of critical superstring theories. For these lectures, it's all going to be type 2b, but the remark applies more generally with n equals 0 or n equals 1 SUSY. And in maximally symmetric 3 plus 1 dimensional spacetime. So Minkowski space, ADS4, and DS. The previous question about quintessence and related things, we're going to first start with maximally symmetric spacetimes. Okay, so that's all we need to do. We need to go from 10-dimensional string theory to a maximally symmetric spacetime and try and understand the physics thereof. Okay, now I've chosen the superstring for theoretical control. There's certainly, you could do interesting things with non-supersymmetric strings, but the game all along is related to this. We want not just weakly coupled, but computable UV completions. So anytime you can make a choice, at least in my world, anytime you can make a choice for more computational control or less, you choose more control. I have chosen, I'm going to choose weak string coupling, large volume of the superstring, and I'm going to work in the setting where I can apply the most geometric tools, namely algebraic geometry tools and related things. Okay, and so that's sort of what's guiding all of this. If you want some like bedtime reading, I put some pages of text sort of how to think about the choices that we make and why we do them this way. And there's no sense in which what I'm presenting to you is the unique or the best way of constructing such things. However, I claim it's the closest route to ground at present. If you want to build these solutions in the mid-2020s, I think this is actually a pretty good place to be looking. maybe the more general solutions of string theory lie somewhere else. Now, you might say, why are we doing extra dimensions? Couldn't we just have an internal CFT? Yes, you certainly could. But we evolved to navigate in space, and that has given us certain abilities that we can't directly apply to CFTs. And we're going to be using that extensively. So it's actually going to be, again, not a physics choice, but a human limitations choice, that we're going to work with geometric compactifications rather than some internal CFT with the same central charge as compactification on the sigma form. Yes, please.
Could that be a reason to think of non-critical string theories as the starting point?
Yeah. So why have I chosen critical string? You can certainly do very interesting things with the non-critical string theories. For my taste, it's really just a question of the level of development of the technology that we have. I haven't yet seen something that seems so great that I could do only with a non-critical string theory that I would want to spend a couple of years building up the tech to do it. But that could happen someday. Maybe somebody else will. I mean, there are famous works on this, of course, and maybe that's a good way. But yeah, we'll be picking critical. So this is just one of these cases where I picked the easy route. OK, great. Other questions about the setup? Yeah. Yeah. OK, thanks. Yeah. So by critical, what I mean is the following thing. Yeah, and thank you. I do hope that everybody will jump in and ask if there's something that I don't define. So the sigma model beta functional for the dilaton looks like d minus 10 over 4 plus alpha prime, and then a derivative of the dilaton in some whatever dimension space-time you're in, and a derivative of the dilaton. Okay. And what we normally do is we say, OK, forget about these terms, and then let's just look at this. And then the discussion of Violin invariance tells you, oh, d has to equal 26 for the bosonic string or 10 for the superstring. And that teaches us that if we want 4 space-time dimensions, then we have to have a central charge 9 internal CFT. That's all if we ignore this contribution. But what you could do is you could say, you could try, so OK, I should specify m runs from 0 up to d minus 1, and d is always the total space-time dimension. And we haven't specified that yet. If I take it to be 10, then I'm done. For a conformal invariance vanishing beta functional, I can't have any dilaton gradients. But what I could try is the linear dilaton. So the linear dilaton is just that phi is a function of the space-time, and it's equal to some Vm, which is a constant vector, xm, which is the coordinate in the space-time. Then the gradient here makes a constant contribution, and it shifts what dimension you can be in. Okay. And so, yeah, we're not going to be doing that, but that's what the definition means. So by critical, yeah, I should say. In all of these lectures, when I say string theory, I will henceforth mean critical superstring theory. Anything else? OK. The string theory yields weakly coupled UV completions of GR. What do these look like? The long wavelength effective field theory of string theory is supergravity. Which contains Einstein gravity coupled to various other bosonic and fermionic fields. Now, let's introduce some helpful terminology. We're going to define a vacuum solution to be a solution of the vacuum Einstein equations. So we talk about string vacua all the time. Let's be very specific about what we mean. So a vacuum solution is a solution of the vacuum Einstein equations. Okay, that is to say it's a pure geometry. Like you're familiar with from regular GR. What do I mean by vacuum Einstein equations? I, of course, mean that the stress energy is equal to 0. Okay, with no sources of stress energy, just the left-hand side of Einstein's equations, i.e. it's a solution of Rmn equals 0, where again, this dimension, so now this dimension m is going to run from 0 up to 9, because after these preliminaries about critical superstring and compactification, we're going to be in 10 dimensions. Okay, so we're going to solve the vacuum Einstein equations in 10 dimensions. Now, a vacuum is a different thing. By a vacuum, I mean a solution of string theory. And so we have a Venn diagram where we have vacua, amongst which are a special subset vacuum solutions. These are non-vacuum solutions. And that's what these lectures are about actually after today. So today is about vacuum solutions. Lectures 2, 3, and 4 are about non-vacuum solutions, specifically flux compactifications, in which the stress energy gets contributions from some p-form fields that I'll tell you about. Yes, thank you. In vacuum, those are the same because you can then. Yeah. Well, so the other term has a g and a Ricci scalar, but then if this one's 0, you trace it, you get an r. R is also 0. Okay, so we want to solve this. Well, let's give ourselves an ansatz. We're going to begin with a very easy ansatz, which is just a product. And by tomorrow, we will make a worked product. So our ansatz is ds squared is g mu nu, dx nu, where g mu nu is going to be, in the long run, de Sitter space. It'll be Minkowski for a while. But anyway, it's the 3 + 1 dimensional spacetime. With minus plus plus plus, of course. And the internal metric is a metric on some 6 manifold. In the long run, it won't really be a manifold. It can have some singularities, but it's going to be some 6-dimensional space, Riemannian. And so y's are the coordinates on the internal space, and x's are the coordinates on the external space. And so m and n run from 4 through 9, and mu and nu run from 0 to 3, just like in special relativity. Okay. So this is just to spell it out, this is going to be a Riemannian metric on some compact Riemannian manifold, which I'll call X6 or big X. So whenever you see X, capital X, that means the compactification manifold.
So is it obvious that the solutions of Sugra are also the solutions of string theory?
Thank you. No, it's only obvious that the vacuum solution. Oh, a couple things. First, I thought you asked something. The question was, is it obvious the solutions of Sugra are also solutions of string theory? 2 remarks. First remark, not the thing you asked. Is it obvious the solutions of Sugra are solutions of just plain GR? Well, vacuum solutions, yes, because that's just the sector. Now, the question, if you found a solution of supergravity, have you solved string theory? Well, that's the question that will remain unanswered, and that's actually the reason for this word. Because what I will do by the end of these lectures is show you, and in the notes and paper, et cetera, a direction of a 4-dimensional supergravity theory that has a de Sitter vacuum in some series of approximations. And if those approximations are valid, which is certainly up for consideration and debate, then this is a de Sitter vacuum of the supergravity theory. Is that a de Sitter vacuum of the string theory? That is a long way to check. The only thing that's really in reach at present is to check more and more carefully that one is deriving the correct EFT and finding a solution of that EFT. So for example, you derive an EFT and you compute alpha prime corrections to it, to all orders, and G-string corrections to all orders, and you find a solution. That's probably a solution of the full string theory, even if you can't compute the amplitudes yet. If, on the other hand, something is spoiled by the first alpha prime corrections, who knows if that's a solution? Yes?
This is a super basic question, but is there
Yeah, the question is why should this be Riemannian instead of semi-Riemannian? We're just going to do a single time here, so we're just going to put our time in the non-compact part. And right, and the other thing I could have done, and I haven't done, is I could have some prefactor f of y pre-multiplying this. That would be warping, and that's going to come later. So we're not doing a warped product today. This, as you may recognize, is a pure Cartesian product of maximally symmetric 3 plus 1 dimensional space-time and a 6-dimensional compact space. Yes?
Is there a reason why there's no cross terms between y and x, or is that an assumption?
Yeah, so if you start to study dynamics, there will be cross terms and you have to deal with it, and it's very painful. And I won't show you. But if you want to figure out kinetic terms for moduli fields, then you have to carefully include those cross terms. But to find a vacuum, not just in the sense of solution, but now in the more colloquial sense of like a static, long-lived thing, there won't be any such dynamics, and you can get rid of those terms. Other questions? Yes. All right. Yeah, good. The question is, why is the internal manifold compact? Answer is, if you have 3 plus 1 non-compact directions, and an additional, let's say, k non-compact directions, and an additional 6 minus k compact directions, then the graviton wave function spreads out in 3 plus 1 plus k. And you don't have any more a 1 over r squared force law. So the short answer is, so that Newtonian gravity arises, you need the graviton to be propagating in 3 plus 1 only. If it propagates in other large dimensions that are large compared to about 100 microns, which is where the tests are, then you're killed.
But by compact, you meant no boundary instead of small.
By compact, I mean that like every open cover has a finite subcover, and et cetera, et cetera. Like that kind of. So it's the formal definition of compact. We will allow some singularities, which could maybe make you think of it not manifold if you think of them as punctures. Okay, yes?
Are you in string frame or Einstein frame?
Almost always Einstein frame. Yeah, question was, am I in string frame or Einstein frame? The answer is, well, this is the, so far I haven't told you enough to specify it. Once we include an overall mode scaling the volume of the internal space, I'll show how to get to 4-dimensional Einstein frame. You should think of this, thank you. You should think of all of this as occurring in 10-dimensional string frame where everything's easy. And then once we get to 4 dimensions, we'll go to 4-dimensional Einstein frame so that the kinetic term will look like r plus dot dot dot, not scalars plus dot dot dot. Okay. Okay, so the vacuum Einstein equation for this ansatz is pretty straightforward. We've already written it. It's that Rmn is 0, and Rmn has 2 pieces. So Rmn equals 0 implies, R mu nu equals 0, and R little m little n is equal to 0. The first of these tells us that ADS and DS are just out, right? Because the only maximally symmetric 3 plus 1 dimensional spacetime with vanishing Ricci is Minkowski. So we can only study Minkowski solutions if we're studying vacuum solutions. That's okay, we're building up. But this second condition tells us that the internal metric must be Ricci flat. So x6 has to be Ricci flat. And at this point, we've explained the first 3 lines. Why we're doing it and hopefully what it means. So what we want to understand now is, how do we get our hands on some Ricci flat 6 manifolds? Now, if you think about it, Ricci equals 0 is just a partial differential equation in the metric. But it's a horribly nonlinear partial differential equation in the metric, and you really don't want to try to solve a compact space. People have tried, no one has succeeded. People have certainly solved it numerically, but analytic solutions are elusive. So, no analytic Rmn equals 0 metric is known. on compact X6.
What about the 6 torus?
Thank you. But, okay, and I have a list of 3 modifications. Oh man, in my notes I said is known on non-trivial compact X6. See? But okay, approximations exist, and numerical results exist. The torus is nice. The torus has a beautiful Ritchie flat metric, and in fact, we all cut our teeth on the torus. This is where you learn to do basic compactification things, because you can handle all the pieces, and on also non-compact cases are known. So that's just to say there do exist non-compact 6 manifolds with explicit and non-trivial Ritchie flat metrics. For example, the conifold or the deformed conifold. These are things where you can just write down the metric, and the metric has vanishing Ritchie, and the spaces are not trivial. Okay. Now our path to RMN equals 0 is going to be via special holonomy. So let me now explain that. This is the only machine currently known to people that can for you the data of Ritchie flat, non-trivial metrics. Not the data of manifolds. Okay. So what is special holonomy? So suppose I have some xn, a Riemannian manifold with the metric, and n is the dimension over the reals of xn, the real dimension n, and suppose I consider some loop. I've got some point P, and starting from the point P, I go around a loop, and I parallel transport a tangent vector around that loop. Okay, so I make a little tangent vector here, and I carry it around the loop, and I see what the parallel transport is. So the transformations resulting from parallel transport form the holonomy group, where I'm going to write this temporarily as the holonomy at P of gamma, where gamma is the connection that we take on the tangent bundle. Now, if xn is connected, then if you have some other point P prime, you try and work out the holonomy group at some other point P prime, well, you can always relate those things by just taking a walk from, and that just creates whatever your group element is. Oh, sorry, I should have said what kind of group is this. This is a subgroup of the natural of the tangent bundle. So look, we're going to assume that this thing is orientable. So the holonomy group is a subgroup of SON because you can just think, the tangent space is Rn, and so as you carry a vector in Rn around a loop, what will it come back to? Some other vector in Rn, but it's orientable, so it has to be an SON action. And if your space is really nice, then the holonomy group can be a really small subgroup of SON like the identity. So for example, a nice torus carries stuff around, it comes back to itself unmodified, holonomy is the identity. Now, because we're going to assume it's connected, I actually don't have to tell you at any point, they're all equally good. And I'm going to take nabla to be the Levi-Civita connection. Then the holonomy with respect to the Levi-Civita connection is called the Riemannian holonomy of the manifold Xn. Okay, and so what we're going to be concerned with now is the Riemannian holonomy of Riemannian manifold Xn. Okay, and roughly speaking, what the holonomy is doing is it's telling you how X is parallel transit. Does it preserve various symmetries? Any questions about that? So now I'm going to tell you, I won't prove to you, but I will tell you the result of a famous classification due to Berger in 1955, which tells us what possible holonomy groups can you get. So this is called the Berger classification. So let Xn be orientable, simply connected, and Riemannian. Then what can this manifold be? It's either a product of simpler things, which will reduce the problem to a later case. Okay, so we discount that. Or it's a symmetric space. A Riemannian symmetric space is just the quotient of one Lie group by a Lie subgroup. And that's not a case that's interesting to us. Or one of the following holds. And this is the classification that's going to help us to organize all of our thinking about vacuum solutions of string theory. First case, the generic case. The holonomy, the Riemannian holonomy group is equal to SO n. That's the generic case. That means the manifold doesn't have any nice structures. First interesting case, the dimension is even, and the holonomy group is equal to UM, which sits inside SO2M. So the holonomy is unitary. Sits inside, it's a proper subgroup. Case 3, n is equal to 2m, and the holonomy is equal to SUM, sits inside SO2m. This is going to be 7 cases. Case 4, n is equal to 4m. I like all the cases, but we're only really going to use 2, and 3 today. But I'll tell you all of them because it's sort of fun to have the list. The holonomy is SPM, which sits inside U of 2m, which sits inside SO of 4m. I'll give names for these things, but let me just write all of them, and then we'll go through the field guide to holonomy. I haven't said what special is. I introduced the word in a preamble, but the definition will come once we've stated the list. 4, 5. Now we're getting sort of exotic. These ones are cool, but we don't need them, except as descriptions of the moduli spaces. Now, you might say, what is this symplectic group? Well, you know what the symplectic group is, but you also know there's 2 different definitions of the symplectic group. This is the definition of the symplectic group where SP1 is SU2, if you want to check conventions. Like, do I put a U in front of it, or is there a factor of 2 inside? This is the convention I'm using. Holonomy is SPM times SP1, which is not in U of 2m, but it is in SO 4m. 6. And now the really weird ones. N is equal to 7, only 7. And the holonomy is equal to G2, which is a subgroup of SO7. And finally, n is equal to 8, and here it ends. The holonomy is equal to spin 7, which is just the double cover of SO7, and that's a subgroup of SO8.
There's no conflict between 2m, 4m, and 8. Like, are those things for m not equal to 4, m not equal to 2, for points 3 and 4?
Oh, these, so let's say, okay, the question is about 3 and 4. So it is the case that, for example, these are compatible. So this is actually a subcase of that. Yeah. This is not a subcase of the. So it's not, from the dimension alone, you can't necessarily read off what property the manifold has. You sometimes have to check more details of what the manifold is. Yes?
This is simply connected, and are we assuming that our spacetime, our Riemannian manifold is simply connected?
Yeah. Sorry, I should have added that over here, but I stated it only as the list of assumptions here. It's important. It needs to be simply connected so that you can then convince yourself that way the holonomy group itself is connected, rather than having disconnected components corresponding to different winding sectors. Sorry, if it wasn't clear, the question was, are we assuming it's simply connected? Answer, yes.
We're also assuming it's connected, right?
Yeah, correct. We're assuming it's connected and simply connected. Yeah, good. Okay. Yes.
Sorry, I mean, do you have a character which tells you which case you are in? Or?
Yeah. Okay. Question is, how do you tell which case you're in? And one thing you can do is you can try and compute various topological invariants and determine which kinds of these things are possible. Yeah. There's another. Yeah. No, so if you relax, okay, question is, what about non-simply connected? Answer is, you can explode the number of possibilities if you start to relax these various restrictive assumptions up here. And it's not that we don't care about them at all, but this is actually a nice place. And I haven't told you at all this is a nice place, because this may seem like it came out of absolutely nowhere. Because like we were talking about Ricci flat, and now for some reason I'm telling you about the classification of possible special holonomy. Why am I doing that? Because this is the way that we get Ricci flatness. So here, RMN equals 0, and here, RMN equals 0, and here, RMN equals 0, and here, RMN equals 0. Each of these is a statement about a manifold and its given Riemannian metric. And so the metric that has this holonomy is the metric that is Ricci flat. So all the cases marked in yellow are cases that actually furnish Ricci flat metrics. So that means if you can check a topological condition, which is what's the holonomy, then you're guaranteed there exists a Ricci flat metric. These things have lots of other ways of interplaying with each other. I won't delve into that. But let's just talk about the most important case. So 2 is called Kähler. I'll say a little bit more about Kähler things. 3 is called Calabi-Yau. And 4 is called hyper-Kähler. This is called quaternionic Kähler. This is called G2. That's called spin 7, but we don't need those ones. And what we're going to, class 3 is a subset of class 2. Right? You can see that this is a special case of the above. And so Calabi-Yau manifolds are Kähler manifolds. And they're Kähler manifolds that have vanishing Ricci. And so our game is going to be to find manifolds with holonomy. So what do we want? We want n equals 6. So therefore, equals 2 times 3. So we want to consider case 3 with m equals 3. And holonomy equals SU3. So from this list, we see that a way that we can get a Ricci flat 6 manifold is to take it to be a holonomy 3, holonomy SU3.
We have to n equals 6 be 2 times 3.
Did I write 6? Yeah. This one I can't justify from my notes. Thank you, Oliver.
When do people ever care about 6 or 7? Because we have to compactify to get 4 dimensions.
Yeah, you can. Very good. Question is, what about 6 and 7? This one is more interesting because you might have heard of M-theory compactified on G2 manifolds because M3 is 11-dimensional. Here you got a 7 manifold. You can get 4D equals 1 supersymmetry by compactifying one of these. Good. All right. So now, how exactly do you see that these things are Ricci flat? Well, I can't really tell you in the course of this lecture. I mean, I can give you some sort of hints, but the statement that manifolds with holonomy SU3 have vanishing Ricci is the content of Yau's theorem, and you got the Fields medal for that. And so that's not like it's not a short thing. Even with the intervening 45 years, it hasn't gotten any to summarize it. Yes, there's a question in the back. Yeah.
But I was going to ask if you would clarify, like, so you're saying that we actually know in cases 3, 4, 6, and 7 that if you're in those cases, you are Ricci flat?
Yes. Yeah. The question is, in these cases, is the metric Ricci flat? And the answer is yes. It's proved by actual mathematicians, case by case. And so yeah, this is definitely true. Now, there's actually a relatively straightforward way of seeing the necessity of it, let's say for this case, and I give the necessary argument in the notes. The sufficiency is Yau's theorem, and so you have to do a little bit of hard analysis to see that. Now, there's a slightly cheaper way of going at it, which is done beautifully in Green, Schwartz, Witten. I won't try to reproduce it here, which occurs based on the following fact. So there's another important fact that I do need to tell you. So let's just talk about Calabi-Yau threefolds for a minute. So a Calabi-Yau threefold, which will denote CY3, is a compact, complex, Kähler manifold of holonomy SU3, and it has some properties vanishes. There exists a nowhere vanishing 3-0 form on the space. Those are the ones that I haven't already stated. The first chosen class is just 1 over 2 pi times the cohomology class of the Ricci form. Decorate the Ricci tensor with some dz and dz bars. Yes?
So you said that no non-trivial examples are known. Does that mean that there's no Calabi-Yau threefold other than like the torus where the exact metric is known?
Correct. Yeah, correct. Question is it really the case that no exact metric is known? The answer is yes. The cases where an exact Calabi-Yau metric is known are the torus, non-compact cases like the conifold, and then for compact models like this, Yau tells you for sure it exists, and you can get numerical approximations. And in very special cases done by Kotru, Zimmet, and Tripathi, you can get some analytical approximations, but not that close, ultimately. Can you repeat the question? I heard the words, but I didn't understand it.
So you said, oh, we have a torus and these are trivial examples, but they have a lot of group.
Yeah, okay, the question is, what's the holonomy group in a trivial case? So it's a little bit of a definition.
Oh, okay.
If I just said that the holonomy group is included in SUM, the torus has the identity of SUM, and so trivially Calabi-Yau, but like that's not the interesting case. So sometimes you have to ask people, like, do you really mean holonomy SU3, or do you mean a subgroup or subgroup of SU3?
It's the latter, you mean?
It's the latter.
Yeah, okay.
Okay. So what are we going to do with these things? So, yes?
People might not know what like 3, 0 form is. Like, what is
Yeah, okay, thank you. Thank you. Okay, so Oliver's remark is I should tell you when I put a one number, comma, another number in parentheses, what do I mean? I mean how many dz indices it has and how many dz bar indices it has. Okay, and so I'm happy to say more about this. We have a very detailed explanation of complex geometry, Hermitian and Kähler manifolds, and complex structures in the notes that spell out what this means. But yeah, thank you. I should say that. Okay, so I won't go through all of those things on the board, but I'm happy to state them in response to questions. Now, there's another fact about these Calabi-Yau threefolds that should be mentioned. Here's a fact that, but just has to do with Lie groups, or Lie algebras. SO6 is the same as SU4. And if you've got a 6 manifold, remember these are always 6 manifolds. They're called threefolds because you count over the complex numbers. There's 6 manifolds. SO6, they would be like if you broke them and made them all junky and lumpy. And so this is the generic holonomy. And we're told the holonomy is SU4. But 4 is 3 plus 1. And that means that the holonomy SU3 sits inside SU4 in such a way that it leaves one singlet. So 3, there exists a singlet spinner. And what I mean by that concretely is there exists a covariantly constant spinner around the space. So if your theory is born with some nice spinners parametrizing supersymmetry, then when you reduce, for each spinner you start with in 10 dimensions, you get 1 in the low dimensional theory. Question, yeah?
So here we did not assume compactness, but it was Ricci flat. But compactness can induce some curvature, right?
If I take the question is if I take something that's non-compact and compactify it, I'll induce some curvature? That's possible.
I do one
Yeah.
compact,
Yeah.
it will not be Ricci flat.
Here we're interested in this for the case that's compact. Although you can apply it for the non-compact case, but let's imagine we're restricting to compact for here.
Are the Turing class and Ricci tensor vanishing independent statements?
No. Yeah, question was, are these vanishing Ricci tensor and vanishing first Turing class independent? The answer is no, because from the Ricci tensor you can make the Ricci form which defines the first Turing class. And so, but the remark is, if someone just tells you the Ricci tensor vanishes, you might be like, okay, but what is that? Is that an invariant? But once you make up the first Turing class from it, first Turing class is an analytic invariant. It's invariant under even substantially large changes of the metric. And that actually, we spell out some aspects of this in the notes. That's one way of seeing why vanishing, why it's one way of understanding the necessity of vanishing first Turing class. Well, okay, sorry. What I meant to say is we spell it in the notes, the connection between the vanishing of the first Turing class and the necessary condition for there ever being a Ricci flat metric. Yes? Yeah. Yeah, thank you. So the question is, why is there a singlet? So you imagine that you have something that transforms, you've got some vector or spinner or whatever that transforms under SO6 or SU4, and imagine you have something that's in the 4. Okay, so now I have my space, which has holonomy SU3. So here's my Calabi-Yau. And I start with some spinner, which is living in the 4, or spinner or whatever, some object that lives in the 4. Now I start moving this thing around. The holonomy is SU3 subgroup SU4. And so there's one direction in this 4 space that is unmodified and 3 directions that get moved around. The one direction is the singlet. That one singlet, you can do beautiful things with it because you can take that singlet, let's call it let's say it's a spinner, and you can take that singlet and put it around anti-symmetrized gamma matrices and make forms. So what I've written here are eta transpose gamma ij antisymmetric eta and eta transpose gamma ij k eta. And you know, bilinear pairings of spinners with gamma matrices inside make p forms, differential forms. This is a 2 form, this is a 3 form. This is actually, I erased it. This is the everywhere constant 3 form. And this is the so-called Kähler form that defines the Kähler metric. So there's a tight connection between the singlet and the geometric structures. Now, I have what, 6 minutes, right?
No, you have until noon.
Oh. All right, I was counting an hour, which is wrong. Okay. So now, what do we do in the remaining 21 minutes? Well, we're going to talk about problem, okay? So we've gotten up to here, the known Ritchie flat manifolds being Calabi-Yau threefolds, and we want to know that they have many moduli. So what is a modulus? Okay, so problem. There exists a moduli space of metrics G such that RMN of G equals 0. In other words, you pick some manifold, you check that it has holonomy SU3, good for you, you know that it has a Ritchie flat metric. But actually, in general, that doesn't fully specify the metric. Change the various cycles while keeping them. You can change the size of the even dimensional cycles and the odd dimensional cycles. So, example. Suppose Ritchie suppose they have some metric that has vanishing. Okay. Vanishing Ritchie. This is an incredibly important mode called the breathing mode, or sometimes we'll call it the volume modulus. And it's the easiest one to see. The condition that Ritchie is 0 is invariant under rescaling up the whole space. Now, there's lots of other ones that are counted by the dimensions of some. What I'd like to do in the remainder, rather than dragging you through the complete computation of what these other moduli are, I'd like to talk about the physics of the other moduli. And, physics of all. So let's take this the following way. We're going to view this as the canonical example of a modulus. You put in your head as the example, as the modulus we're thinking about all along. And if you want to know why are there many moduli, you can look at the notes and come ask me. And there we spell in detail the counting of all the other that you can make. Okay, so what I will state, however, is the overall summary without giving the proof here on the board, so we can talk about the physics of moduli. And the overall statement is, so result, the Calabi-Yau threefold metric has moduli. And the number is, so if we define H, so now getting back to Oliver's remark, if we define the set of del bar closed PQ forms, so what am I doing here? I'm starting with de Rham cohomology, which hopefully you know, and I break up the exterior derivative into a holomorphic piece and an anti-holomorphic piece. And I look at the cohomology of, let's say, the anti-holomorphic one. Doesn't matter. I could look at the cohomology of the holomorphic one. And what I'm going to do is, just like you find de Rham cohomology groups as closed forms, mod exact forms, I'm going to look at anti-holomorphically closed PQ forms divided by, or mod, anti-holomorphically exact PQ forms. And HPQ, the Hodge numbers, are defined to be the dimension of these groups. So this is a Dolbeault cohomology group, and the dimensions of these groups, viewed as vector spaces, are the Hodge numbers. The ones that are relevant for a CY3 are H11 and H21.
So the holomorphic and anti-holomorphic homologies have the same dimension?
Correct. Thank you. Question was holomorphic and anti-holomorphic have the same dimension? Correct. By complex conjugation, you could either use del or del bar. But something like a form that has, 2, 1 is the same as 1, 2, but 2, 1 is not the same as 1, 1 or something like that. Okay. And so in principle, because we're working with complex indices, you can have 3, 0, 0, 3, 2, 1, 1, 2, and 1, 1. Those are the possible, well, you can have also 0, 1. 1, 0, 0, 2, and 2, 0. And these ones turn out to vanish. In the case of a Calabi-Yau threefold, these ones are each equal to 1, it turns out, and these ones matter. Now, let me say one thing, and then I'll take a question. So you may say, why am I ripping through rather than exploring all of it? Well, because the only thing we really need to take away is that if you can compute the dimension of a certain cohomology group, then you can count the number of moduli. And we'll come back later to figuring out the effective theory in terms of these numbers. Okay, question?
Sorry, I think
Yes.
I got confused about it. Because, are these like cohomology groups invariant under complex conjugations? For example, if you replace the partial bar close the PQ forms with the partial close the PQ forms, are they the same group? Or?
Yes. Yeah.
Yeah.
Yeah. Yeah.
Yeah. Oh. Yeah. Okay. I see. Yeah. Thank you.
So D is the number of moduli?
I'm sorry. This D.
Yes.
My apologies. That is the exterior derivative. So this is the exterior derivative, which I've split into a derivative with respect to some z and some z bar coordinate. There's a question in the back. Yeah.
Is H3 0 the
Thank you. No, I should be more specific about this. Let me just write the Hodge diamond. What do I want? I want 1, 1, 2, 0. 0, 2, 1, what am I doing? 0, 3, let's see, 3, 3, 2. I've succeeded in writing the Hodge diamond wrong, so it's not actually a proper, let's see, what do I want here? No, I want 3, 0.
Don't you want all the forms of a given rank on the same row?
I think I do, so I think 3, 0, 2, 1, I think that is what I want, but, and 2, 0, thank you, Oliver, 2, 0, 1, 1, 0, 2, and then you can, that's the part that we actually need here, and we can have 1, 0.
There's 1, 0, 0, 1, and 0, 0.
Yeah, 0, thank you. 1, 0, 0, 1, 0, 0, and then all the way down I can have 3, 3, et cetera, but we don't need them. Thank you. Okay, so sorry, I messed that piece up. So this is just telling us that there's one thing there. This guy's just 1. Now, these manifolds they're simply connected, and it turns out they don't have any 0, 1 or 1, 0 piece, nor do they have a 2, 0 or 0, 2 piece. And a statement that there's a 3, 0 form is the statement I made previously, that there's a holomorphic, nowhere vanishing form of type 3, 0 that you can construct this way. And so actually this number is 1, and this number is 1. And so the only non-trivial numbers, and these two numbers are equal to each other, is equal to 1, 2. So the only non-trivial numbers are these ones. Yes?
The top one was the connectedness of the space.
Yeah. Okay, yes, sorry about that. So these are the ones that we want to keep track of. And it turns out, if you look into examples, that typically they're order hundreds. Okay, so you don't have a two-dimensional moduli space in general. If you really get going, like in the example I'll tell you by the 4th lecture, this one's going to be 150. This one will be 8. So completely modest. So hopefully we've gotten to a point of understanding that these things at least have moduli. what the notes spell out is how do you actually make the moduli? In other words, how do you take the Ricci flat metric and concretely deform it and see that the resulting deformation is, one, counted by these, so we show why it's counted by these using Hodge's theorem and some direct calculations, and two, how do you see that that sort of leaves the metric Ricci flat? Okay. Now, in the remaining time, there's one other thing that we have to talk about. It's actually quite important. Which is that you can also get massless fields from p-forms in the supergravity theory. So let's step back a minute and ask, what is the deal with these moduli? So far we've been talking about them as geometric deformations that leave the Ricci flat.
Sorry,
Yes, please.
is there an easy way to say that and to see that these moduli will be massless?
Yeah, good. That's precisely what I was. Yeah, the question is how do we see that they're massless? And yeah, that's what we'll talk about right now. One thing that you could say is, well, you have the what equations are we solving after all? Ricci equals 0, and these things leave Ricci equals 0. There's no stress energy anywhere, and you make now. You can't do anything you want to these moduli. You have to very slowly move them, and that adiabatically changes the geometry in one place in your spacetime to different geometry in a different place. So, so in a way, the existence of a moduli space is a way of saying there exist deformations that cost 0 energy. Now, there are fancier ways of being sure that this will be the case. In fact, there can't be potential energy if you preserve n equals 2 supersymmetry, which is how much we've preserved. But I think the direct argument just comes from looking at the 4D Lagrangian and seeing that there's no associated stress energy until you give the moduli fields time dependence or space dependence. Then there's associated energy. Yes? Yeah, effectively. Yes, these are like goldstones. Now, the things I'm about to describe are much more like are not quite as protected as we shall see in later lectures. Okay, so, but let's step back and Calabi-Yau compactifications. The details of this geometry aside, what we want to know are what are the light fields in the 4D theory, right? Remember that if you compactify string theory, there's some KK scale, and the KK scale is going to be high, very high compared to any physical scale we're generally interested in. And so the only fields that we care about are the 0 modes, the Kaluza-Klein 0 modes. We're not interested in highly excited internal modes. And so we need to make sure that we're keeping track of all of the 4-dimensional massless fields. And so far I've told you about one very important class of 4-dimensional massless fields, the geometric moduli. In the remaining few minutes, let's talk about the other class of massless fields that you get. Okay. So consider form. Now we're not going to have to keep track of holomorphic and anti-holomorphic indices. With the Maxwell type action, S equals integral d10x square root minus g. G is the metric on the whole 10-dimensional space. F a b dot 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 f upper a b dot dot dot, which is integral f wedge Hodge star f with f equal to d fp plus 1 equal to dcp. Okay, so let's make our hypotheses clear. We're temporarily asking ourselves, suppose I have some p form where p can be any non-negative integer, and we're considering its p plus 1 form field strength with the Maxwell type action like here. So of course if I took p equals 1, this is Maxwell theory. And in supergravity, when I said that supergravity contains gravity plus a collection of other fields, some of the other fields it contains are p-forms. 0 forms, 1 forms, 2 forms, 3 forms, and 4 forms. Okay, so suppose we got that. And let's imagine that we're going to dimensionally reduce. In other words, we're going to take that supergravity theory and we're going to study a compactification on a 6 manifold. And compared to the gruesome calculation of the moduli that we show in the notes, the calculation we're going to do now to get massless fields is actually super easy. Okay, because the equation of motion, just from Euler-Lagrange, is that d star d Cp equals 0. Let me draw all my stars the same way. And the Laplacian is equal to d star plus star d star d. If this is unfamiliar, this also was spelled out in full detail in the notes. Just a convenient way of writing the Laplacian. And we're going to make a gauge choice. The gauge choice that we find to be convenient is d star Cp equals 0. And you should think of this as roughly analogous to Lorentz gauge in E&M. If you, with this gauge choice, then the equation of motion is equivalent to Laplacian of Cp equals 0. In other words, the equation of motion for a p-form is the Laplacian equation, is Laplace equation for p-forms. Okay. Now, let's make an ansatz. We talked about dimensional reduction. We're going to make an ansatz in which Cp is some function of x, well, wedge, well, time, I mean, wedge, but it's trivial because this is a 0 form, some bp of y. Now, I remind you, x is my space-time coordinate, y is my internal coordinate. So I'm basically saying, what if I consider my p-form to be some sort of space-time times an internal p-form? Okay. With this ansatz, oh yeah, I'm going to take bp to be an eigenfunction of lambda. Lambda, of delta. Delta bp is equal to some lambda bp, where lambda is some real number. Pardon me?
The delta BP, is that the 60 delta?
Thank you. Is it the 60 delta? Yeah. Although, since that's the only place where the dependence comes, yes. Yeah, correct. So delta, because we have a product space, delta is delta 4 plus delta 6, which is, since we're in Minkowski space in the external part, that's D'Alembertian plus delta 6. And so now if I look at the equation of motion, delta Cp equals 0, that corresponds to box plus lambda phi equals 0. And so phi is massless if and only if lambda equals 0, which is to say bp is so-called harmonic. I remind you that a harmonic form is one that's annihilated by the Laplacian, 0 eigenvalue eigenfunction of the Laplacian. And so what we see is that massless fields result from harmonic forms on the internal space. And the content of Hodge's theorem is that harmonic forms are also counted by Dolbeau cohomology groups. So, massless field, that's a physical thing. Harmonic form, that's sort of an analytic thing, like it's annihilated by the Laplacian. But Hodge's theorem tells you you can do a topological calculation and count these. That means you can do topology and count how many massless fields you have. It's the same topological computation that counts the moduli. And in fact, supersymmetry is going to pair the fields that we get from reducing p-forms with the fields that we get from reducing the metric. Okay. Yes, question?
We also factored out
one form?
Very good question. Could you factor out or something else? Absolutely, you can, and we do. It's not going to happen much in these lectures because I'll mostly show you the scalar set. You can get interesting stuff by factoring out, a one form here, making this p minus 1 for sure. Okay, so in the remaining minute, let me now just say what's the recap. So, okay, so we started talking about why we want to study geometric solutions. And we're using vacuum solutions as a building block, not because we're ultimately interested in vacuum solutions. And what we saw is that geometric vacuum solutions of superstring theory are Ricci-flat 6 manifolds. And I asserted that the only known ones that are non-trivial and compact are Calabi-Yau 3-folds. And I showed you that these have at least one modulus and also associated massless p-forms. And I asserted that there's actually a lot of geometric moduli. Now, the thing I haven't told you is that massless scalar fields are a problem. I will lead with that next time. We'll talk about why they're a problem. But just in short, they couple massless scalar field, then it can mediate a long-range force. Since these moduli come from the gravitational sector, their couplings are of gravitational strength, so like as strongly coupled as the graviton. You can do a test. The version lunar laser ranging does this. This is the Earth and the moon, and very schematically the sun, and they're both falling toward the sun under the influence of gravity. If there's another gravitational strength force that depends on elemental composition, then since the Earth has a lot more iron relative to silicon than the moon does, you'll get a differential falling. And that will cause their separation to grow. The Earth-Moon distance is measured to millimeter precision by lunar laser ranging. The Apollo 15 experiment, Apollo 11 put a retro reflector there, and you can shine a powerful laser off it, get millimeter level measurement, and get sort of 1 part in 10 to the 14 constraints on equivalence principle violations. And it's really hard to write down a theory as moduli that are super light, like they can propagate over Earth-Moon distances, and that don't violate the equivalence principle at an extent. So for that reason, what we need to do in the next lecture is go away from vacuum solutions, find non-vacuum solutions in which the moduli become massive, and then the solutions are possibly realistic. Okay, I'll stop there.
For lunch, I just wanted to make a comment about Sasha's lecture this afternoon. Because the hymn writing on the blackboard over Zoom was a little tricky to see yesterday, we're switching just to him writing on a tablet today. So I'm hoping that's going to be a little more visible. So we've been experimenting with it, so thanks for bearing with it. Hopefully it'll be more visible.